All right, physics fans, we have a very important topic here. This is going to be a video introducing the concept of acceleration. That's a really important concept in physics. You probably know the word acceleration and what it means to accelerate, but the way it is defined in physics might make it a little different than what you think of currently. So pay close attention to the way we do this in physics and the way it's defined. In this video, I have word definitions, some numerical examples, and also some examples involving a graph. This is where we are in this unit on kinematics, and acceleration is the last of 6 really important concepts for kinematics. These are numerical quantities that we need to be able to describe and define and calculate. And acceleration is the last one, arguably the most important one. You're going to see later in physics, to understand forces, which is one of our major topics in physics, we need to understand acceleration. So here's our objective: be able to distinguish and apply the concept acceleration and the various types of acceleration, if you will, words like average or constant and so on. So we're going to start with an example that I bet you've heard of before. So people talk about the acceleration of a car. If they're car shopping, they might find out, oh, what's the 0 to 60 time? I bet you might have heard of that. If not, well, you can find it in numerous places. So people would say, this car can go from 0 to 60 in 15 seconds. Now, is that impressive? Well, if you're familiar with cars, you would think, no, that's not impressive. That's actually not very good acceleration, 0 to 60 in 15 seconds. If you could do a better acceleration, what would happen to the time? Well, I bet you know the answer to that question. If I can accelerate better, I'll get to 60 miles per hour in less time, maybe 10 seconds. So if I went from 0 to 60 in 10 seconds, that would be a better acceleration, greater acceleration than 0 to 60 in 15 seconds. Well, in physics, we don't want to describe acceleration by saying how many seconds from 0 to 60 miles per hour. That's kind of awkward. So what we do in physics is we define a particular value. But notice that what happens in these quantities, the more rapid the increase in speed, the greater the acceleration. And we want to be able to put that into a single numerical quantity. So how do we do that? Well, there's a rate here, and we just need to define a rate, and then we would be able to put a single numerical value on the acceleration of an object. Here's our definition in words. Acceleration is the time rate of change in, and then I purposely left that hanging. What is the correct way to finish this statement? Well, if you didn't know physics, you might think speed, but that is not correct. In physics, we define acceleration in terms of velocity. So finishing up that statement, acceleration is the rate of change in velocity. It has to be velocity, not speed. And there are reasons for that I won't get into here, but this is the way it is defined in physics. Velocity is a vector, and that makes acceleration a vector. Symbol for acceleration, universally accepted as lowercase a, with the arrow there to indicate that it's a vector quantity. The acceleration vector is giving us the rate of change in the velocity that's occurring per unit time, but also the direction of the change. So by defining acceleration as the rate of change in a vector quantity, acceleration has a direction itself, which would point in the direction of change. And then here's the part that's a little bit odd. So before you take physics, to accelerate would mean only one thing in your mind, and that would be go faster. If I accelerate, I go faster, obviously. That would be an increase in speed if you go faster. But if we think about this definition in words, Acceleration is the rate of change in velocity. It does not say anything about going faster or increasing in speed. So any sort of change in velocity would be a type of acceleration in physics. So that includes an increase in speed like you would expect, but also a decrease in speed. If your speed decreases, then your velocity would be changing, and that would be a type of acceleration. Now, I bet you're thinking, oh, we got a name for that. We call it deceleration. Well, yeah, we can use the word deceleration in physics, but we don't really have a separate quantity defined as deceleration in physics. So we're not going to have a separate symbol, a separate word definition, a separate equation for a decreasing speed. We can still use the same definitions and same symbols for acceleration to describe a decrease in speed. So anyway, a decreasing speed is a type of acceleration, you might say, in physics. Now, if you're looking closely here, I hope you notice there's a little comma after that. There is a third kind of change that can also be a type of acceleration and is a type of acceleration. That is a change in velocity in which your speed does not change. What else is there, you might say? Well, velocity includes a direction. So if you have a change in direction, that is also a type of acceleration in physics. So all three of those things are going to come up as you continue to study physics. But they all are basically contained in this definition, this simple definition. Acceleration is the rate of change in velocity. If we go back to my example, a car, your car has a pedal for going faster. That's sometimes called the accelerator pedal, right? The gas pedal. So imagine you're driving your car and you put your foot on the gas. Whoa! Then I'm accelerating and I have an increase in speed. But in physics terms, the brake pedal would also be a type of accelerator. I guess you could call it a decelerator. But it causes a change in velocity. So the brake pedal, oh, I'm stopping, will cause an acceleration. It would be a type of acceleration. And then the third accelerator in your car is the steering wheel. So if I turn, even if I'm cruising at a constant speed, that is a type of change in my velocity vector, and that's a type of acceleration in physics also. That's one that we'll get into more detail later in the year. There are some equations for determining acceleration, and they're based on the definitions, the definition for rate of change, and it works just like the formulas for velocity pretty much. Average acceleration would be delta v over delta t. If we know an acceleration to be constant, then we might drop the word average from our description. And then we would simply have acceleration is delta v over delta t. Notice that this is pretty much the same formula as we have for velocity, just different letters. So average velocity is delta r over delta t. Average acceleration, delta v over delta t. The delta means final minus initial. So sometimes you will see the same formulas written in that format, final minus initial. So here I have the same formulas, and instead of delta, you might have to calculate change in velocity by subtracting final velocity minus initial velocity. Just kind of depends on the context. You'll often see physics formulas in different forms. So this is a common form for acceleration. You might see this depending on where you look. So we started this discussion by thinking about a car going from 0 to 60. So let's determine the acceleration using that formula and imagining a car going from 0 to 60. So I've created an animation and watch what happens. I'll start my animation. And I'm looking at a speedometer of a car, and as the car moves faster, that speedometer is showing more and more miles per hour as the car is going faster and faster. Obviously, that's a type of acceleration. If the car went from 0 to 60 in 10 seconds, then I could calculate final velocity 60 minus initial velocity 0 divided by the time 10 seconds. That's a change in velocity of 60 miles per hour per 10 seconds time, and then divide 60 by 10, and that would give me 6. 6 what? 6, well, in this case, 6 miles per hour per second, which might sound funny, but it actually makes perfect sense. If you think about what was happening with the speedometer was going up. How much? 6 miles per hour per second for 10 seconds, ending at 60 miles per hour. Does that make sense to you? I hope so. And then that would be our acceleration. Now, we don't often use miles per hour per second in physics, but that would be a valid example of calculating an acceleration. Acceleration is a vector, so the direction of change in my animation anyway, the car is moving to the right or east, and the velocity is getting greater and greater in that direction. And therefore, as a vector, the acceleration vector of this hypothetical car would be 6 miles per hour per second east, or towards 0 degrees, or to the right. So here's your first example of what acceleration looks like in physics. Not 0 to 60 in 10 seconds, but this quantity, this vector quantity, 6 miles per hour per second, 0 degrees. I have some more ways to illustrate this. So let's watch the animation one more time, but now I have a table. So consider what happens in this table. I'm going to run the animation again and think about this idea. Okay, acceleration is the rate of change in velocity. It's describing how rapidly the velocity is changing. So every second that goes by, my speed is increasing by a certain amount, well, by 6 miles per hour. And that 6 miles per hour per second is describing the pattern of numbers that you see in the table. Every second further in time, my speed has increased by another 6 miles per hour. And then it makes perfect sense to say, okay, that's going to be the rate of change in those values. So I hope that that helps you to make sense out of that. The miles per hour per second units makes perfect sense. But typically in physics, we don't use miles per hour. We often use meters per second. In fact, that's what we almost always do. What if your car had a speedometer in meters per second? Well, I've never seen a car like that, but you could. So notice what I did here. I have my same animation, but I have changed the units of my hypothetical speedometer. So this is a speedometer that would be showing how many meters per second the car is traveling, the rate at which it's traveling. And if I run my animation, what you'll notice is the speed increasing by 2.68 meters per second every second, ending at 26.8 meters per second. Now, 26.8 meters per second is equivalent to 60 miles per hour. So going from 0 to 26.8 meters per second is equivalent to going 0 to 60 miles per hour. And if that occurs in 10 seconds, then change in velocity 26.8 meters per second divided by the time 10 seconds would give me 2.68 meters per second per second. Or I've rounded it off here, we'll call it 2.7 meters per second per second. Now that is getting closer to the way we typically show acceleration in physics, although if we look at the way that's written, it's kind of awkward to look at, right? It's also a little bit awkward to say and annoying, 2.7 meters per second per second. You got to put a pause in there or it really sounds weird, 2.7 meters per second per second. But it should make sense to you. 2.7 meters per second is how much change occurred per second. So it's basically the same thing as the concept where we had the number of miles per hour per second, but now it's meters per second per second. Well, meters per second can be simplified and rewritten in a more compact form. Meters per second squared. So you can, hopefully you could convince yourself of that if you divide meters per second by the quantity seconds, you get meters over seconds times seconds, or meters per second squared. And that's the way we usually say it. Now, it doesn't actually make as much sense if you say it, meters per second squared. What is a square second? Well, there's no such thing as a square second. But this is a more convenient way to write it. It's also a more convenient way to say it. So that's what we typically do in physics. So here is an example of acceleration the way you would often see it in physics. I have here a graph showing velocity versus time for a hypothetical object. And if acceleration is the rate of change in velocity, then we can judge acceleration by looking at this graph. Notice the graph shows the velocity as being towards the left. Well, that's not what was happening in the previous animation. This is not intended to be a graph of the car in our previous example. So this is just some object. This could be a bicycle, say, going by. You look out the window and there goes a bicycle moving to your left, and you graphed the velocity of the bicycle as it went by. Well, if we look at this graph and we think about our definition, acceleration is the rate of change in velocity. Well, hopefully you might realize, hey, the slope of this graph is going to tell us something. The slope on any graph is delta y over delta x. That's always true. But on this graph, that would be delta v over delta t. Change in velocity per change in time. So what does that mean? Well, that means if we have this graph, then we can view acceleration as equivalent to the slope. So this would be a different way to think about acceleration. Acceleration would always be the slope of a velocity versus time graph for linear motion. Now, if we have two-dimensional motion, it would get more involved. But again, we're kind of sticking mainly with linear motion in this introductory unit on kinematics. Let's find the acceleration for this hypothetical bicycle going by. So we know how to find a slope. I could read 2 points on the graph and find the slope using those 2 points. At t equals 2 seconds, the velocity was 3 meters per second to the left. At t equals 5 seconds, the velocity was 9 meters per second to the left. And then I can calculate slope. This would be a positive slope on this graph. That would be 6 meters per second increase in velocity to the left, occurring in 3 seconds time. So that's 2 meters per second increase in the velocity as a description of how the velocity was changing. That would be the acceleration. So the acceleration illustrated by that slope would be 2 meters per second squared to the left based on the way the graph is described as a velocity pointing to the left. If you have a linear graph, that would indicate a constant acceleration. That one comes up not constantly in physics, but often in physics. We'll have some need to determine whether or not an acceleration is constant. So a linear velocity graph is one way to tell, the best way to tell really, that acceleration would be constant. So if we have a nonlinear part of the graph, we can use the concept of the tangent line. If we draw a tangent line at a particular point and find the slope of that tangent line, that's going to give us a rate of change in velocity that applies to the instant that we have chosen. So this point where my line is touching is the point of tangency, and the slope of the red line matches the green curve slope at that instant. So what we say is that the object would have this acceleration at that instant in time on the graph. So this would be an example of finding an instantaneous velocity, or not velocity, this would be an instantaneous acceleration based on a velocity graph. The instantaneous acceleration at that instant, time equals 7 seconds. The graph that we have here ends with a plateau. Well, the slope of that plateau would be 0, horizontal line. So what does that tell us? Does that mean our object has stopped moving? Actually, it does not. That means our object has stopped accelerating. But notice there's a certain velocity there at that instant and during that interval. And once I get to that, it's a plateau at a certain velocity. So that's at about 13 meters per second. My object is moving at a constant velocity. Maybe the bicycle was cruising at 13 meters per second to the left, and it did that for a couple of seconds without changing. That would be no acceleration, 0 acceleration, and a constant velocity. So if we look at this graph, we can notice a curve at the beginning, and then a straight line, and then another curve, and then another straight line. And we can interpret what's happening to our object by thinking about those types of functions shown. Wherever we have a line, that's a constant acceleration. So from t equals 1 second to about t equals 6.2 seconds, our object is accelerating constantly with a constant rate, not just always accelerating, but in physics, if we say constant acceleration, that means the same acceleration. So a constant value of acceleration is shown by the linear graph. Where I have the curve is something you need to think about carefully to put it into correct words. So it seems like it's slowing down looking at the slope, but that doesn't mean our object is actually slowing down. Our object is continuing to move faster and faster because the velocity is going up. But the slope is getting less, means that the acceleration is getting less. So this would be a region of the graph that's kind of interesting. This would be a decreasing acceleration because the slope is getting less, but it's an increasing velocity because the speed is increasing, moving faster and faster according to the values shown on the graph. So at the beginning of that interval, our object is going about 11 or 12 meters per second, but by the end of that interval, it's going faster at 13 meters per second. Acceleration is not a measure of how fast you're going. Acceleration is the rate at which the velocity changes, and that's something different. So it's an important value in physics, but acceleration is not a description of how fast you're going. How fast you're going is described by the concept speed or velocity. Acceleration is describing how rapidly that thing is changing. At the end of this graph, you have no acceleration, 0 acceleration, and a relatively large value of velocity. And that's the way acceleration goes. You can have a non-existent acceleration while you have a great velocity, and vice versa. You can have a very high acceleration and a very low velocity, or 0 velocity. So acceleration is a separate quantity. It's a very important quantity. I hope that this video has helped you to start to understand the way we use the word acceleration in physics.